Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Okay, hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A Paper 3 from 2020. This part's about two practical procedures used in organic preparations. Complete the missing labels on the diagram and name the techniques. So this is a condenser. It's showing an arrow pointing to this thing, and then one coming out here. So we put water going in and it flows up and then out like that, because it doesn't accumulate, and make sure that it's constantly keeping it, cooling as it's going along. Otherwise it'd be like cooler, warmer, and that's not really useful. So we put water in at the bottom and then water out at the top. And then the name of it is a condenser. There you go. Name of technique. So what we're doing, we are heating something, we're letting it rise, and then it condenses and it falls back down. That is reflux. So what we're doing is we are refluxing, and I've also forgotten to answer this one here. What is that thing? That is a pear-shaped flask. There you go. And that's all of them. Cool. Now it says to draw a labeled diagram showing the apparatus for filtration under reduced pressure. So what you need is a Buchner flask. So in order to filter under reduced pressure, you need to be able to reduce the pressure while you're filtering. What I mean by that is that you are going to use a Buchner flask. The reason being is because you can attach a vacuum pump here, right? And what that will do is it will draw air out here, creating a suction force like that, or a tension. So then what we are doing is we're filtering. So we're going to put our filter funnel here. We're going to make sure that that's sealed, so it's not like, sucking air out from the atmosphere. And then we're going to draw like the other part up here, which I've again horrendously fumbled. We're going to be using a Buchner funnel, and we're going to draw this dotted line here and label that as a Buchner funnel. And this is a Buchner flask. And there you go. That's all. This part's about amines. It shows the structure and boiling points of three amines, which are structural isomers of C3H9N. Explain the differences in boiling points. So when you're boiling something, you are breaking, what we're breaking forces between molecules. We are not breaking covalent bonds. This comes up year again, and people don't learn. If you are breaking covalent bonds, you are literally breaking this into chunks. You are no longer having this. If I melt ice, for example, right, I still have H2O in each water molecule. It's not like I've broken it into H and O. It's because you're breaking forces between the molecules, intermolecular forces. So here, we're breaking forces between these. So we need to look at the intermolecular forces we're actually breaking, here, and what explains why, some are higher than others. So here we can see there's an NH2, so there's got to be hydrogen bonds here, as well as the fact it has London forces. NH as well, so this has to have hydrogen bonds and London forces. Here, there's no N to an H, so that means it's London forces only. This has the lowest boiling point, and now we've just pointed out that it only has London forces. So that means that the CH3N has the lowest boiling point because it only has London forces, which are weaker than hydrogen bonds and require less energy to break. We're not breaking covalent bonds, right? Now we need to explain these two here. So this one has higher than this boiling point, but this one is the highest. Something about these two are different. They both have NH2, so they both have hydrogen bonds, right? But if we think about it, this is branched, this is not. The only explanation has to be something between this versus this. And what it is that this branched makes it harder to stack them, because if you think about it like this, you can stack loads. There's more surface area for contact between molecules, which means the London forces would be stronger, because London forces are affected by the number of electrons and also the shape of the molecule, whether you've got more surface interaction. So in this example here, the CH3, 2, CHNH2 and the CH3, CH2, CH2, NH2 have higher boiling points than the CH3, 3N, therefore, because of the hydrogen bonds, right? But then we need to talk about these two. Well, it must be that this one has stronger London forces. So that means the CH3, what was that? CH3, CH2, CH2 has a higher boiling point than the CH3, 2, CH2, NH2, because it is straight chained and therefore has more surface for contact between molecules and therefore has stronger London forces. There you go. So if you do it like that, where again, melting boiling points, all of that jazz, you're looking at what bonds you're actually breaking and comparing them. You're not breaking covalent bonds. The only time you ever do that is if you're boiling like diamond. Amine A is a liquid at room temperature and pressure. When vaporized, 0.202 grams of this amine produces this much gas at that temperature and pressure, and the carbon-13 NMR spectrum has 3 peaks. Determine the molecular formula of A and suggest a possible structure. Step by step, let's collect the information. So we need to first of all figure out what the molecular formula. They've given us the mass and a whole load of other information. PV equals nRT. We can work out N, use its mass to find the MR out. So then I can rearrange this to get N equals PV over RT, and then we can sub the numbers in. So it's 1 times 10 to the 5 pascals times the volume. That's in centimeters cubed. We need to make it meters cubed. So you're going to do 72 divided by a million, or times 10 to the minus 6, all over R, which is 8.314, times the temperature in Kelvin. That's in degrees C, so you need to add 273. So the temperature here would be 373. If you do that, you get moles of 2.32 times 10 to the minus 3 moles. And remember, this is the moles of this amine. We know the mass of it, so we can work out the MR of this amine, A, which is going to be MR equals mass over moles, which would be 0.202 divided by the 2.32 times 10 to the minus 3, which gives us this 87 here, right? Now, right, we know that NH2 of this will have been dedicated to the amine, so I can do 87 minus 14 minus 2 to figure out how much CHs are left, which is going to be 71. Now, the CHs are probably going to be broken off with CH3s, so I can remove a 15 off of that, and the rest will be CH2s, which is 56. So a CH2 is 14, so if I divide that by, so each CH2 is 14, so then 56 divided by 14 gives you 4. So now I know that this thing has a CH3, 4 CH2s, and an NH2, and that gives you the total. So the formula of this thing, the molecular formula, has to be, well, carbon and 4 carbons, it's got to be C5H. So there's got to be, so 4, there's 8 of those, there's 10, and then there's 3 more, so 13, H13, and then it's got to be N. But they also want the structure of this thing. The number of peaks tells you how many carbon environments there are. So there are 3 carbon environments, but there's more carbon atoms than there are environments. Whenever you have a scenario where you've got more atoms than environments, you're probably going to have duplicate environments, as in like you're going to have symmetry in this. If it's an amine, then I'm going to start with its N, and it's going to be NH3, but you swap some stuff out, and I'm going to see how I can divvy up all of these 5 carbons to make sure I have 3 environments. I want to make sure that I make some of them the exact same to each other. So here again, let's have a look. I'm going to start with my N, and I need to divvy up all of these so that I have 3 environments. So what I could do is I can make 1 carbon with 1 environment. That's 1 environment down. I'll have 2 left, right? And those other 2, so if I give 1 environment to 1 carbon, then I'll have 2 environments left for 4 carbons. So these 4 carbons can share 1 environment each. So 1 environment for 2 carbons, 1 environment for 2 carbons, right? Is what I'm trying to get at. So I need to try and divvy all of these up some way. So what I could do is I can have, NH3 likes to chill, and you can swap off some of the H's for stuff, right? So what if I just said, like, for example, we have an N here, and I put a C over it. So that's my first environment gone. I need to use up, so I've used up 1 of my 3 environments. I've got 2 left. And remember, I can only share 1 environment between 2 carbons. So if I put another carbon here, that's another environment, but I'm only allowed to share 1 between 2. So I'm going to put 2 carbons here. If I write the H's on here, CH3, CH3, that carbon and that carbon are identical to each other. So that's 1 environment. This carbon's another environment. Looking good so far. I only have, so we have 1, 2, 3 carbons. I only have 2 carbons left, but they have to share the same environment. I could just put H3C here and H3C here, because now that's 1 environment, but that's the same as that. That's a different environment, so that's environment 2, and these 2 are the same, so that's the 3rd environment. And there you go. So that's kind of how I do these. So the amino acid, this can react to form a cyclic compound with this formula and 1 other product, complete the equation for this reaction. So we have an alkene here, we've got a carboxylic acid, we have an amine. In my head, cyclic means that this has formed a loop somehow, right? The options are this will have reacted with something, but it's only reacting with itself. There's nothing else being added. So that's not going to do any reacting. However, you got a carboxylic acid and an amine. Those 2 can react to form an amide link. So what's happened is it's self-polymerized via condensation, which means it will have booted out an H2O. So when you do this, the easiest way to do that is to draw the amide link, because an amide link will look like that. C double bond O and H, and then just kind of put the pieces together. So this carbon was with a carbon here, which was double bonded to this carbon here, which was then single bonded like that. And each of these have a hydrogen on them like that. There you go. That's how you spot that. Every time you have an amine and a carboxylic acid on one end of each thing, it it will do the reactions that it can, like the polymerizey stuff. So it could polymerize with itself, and you can get cyclic compounds like that. So transition metal ions can bond to ligaments to form complex ions of different shapes. Explain what ligand means, coordination number means, ligand substitution, and then use examples of complex ions of different shapes limited to monodentate ligands. Your answer should include diagrams and equations where appropriate. So all your complex ions have your metal in the middle and whatever, and then it will have these datively or coordinately bonded things coming into it like this, right? 1, 2, 3, 4, 5, 6 of them. If it's dative covalent, the bond, dative means that both electrons came from one thing. So this thing that's giving it has to be able to give 2 electrons to the metal ion, right? The ligand that's joined to it. So if it's able to donate 2 electrons, it must have a lone pair. So a ligand has a lone pair of electrons. It donates to the metal ion to form a coordinate bond. So that bit's dealt with. Now it says coordination number. Coordination number does not mean how many ligands you have, which is a mistake that people make. Because you can have a bidentate ligand, for example, like this. You have 3 ligands, but you still have 1, 2, 3, 4, 5, 6 coordinate bonds. So coordination number is simply just the number of coordinate bonds you have. That's it. So then coordination number is the number of coordinate bonds. Cool. And then ligand substitution, you can't just say ligands are swapped. You need to make it clear that a ligand is replacing another ligand. It's swapped for another. So a ligand is replaced with another ligand. Cool. So we've done that. And then it says using suitable examples of complex ions of different shapes limited to monodentate ligands. So we need to talk about the shapes that we can have. So we can have shapes and our monodentate ligands. We could have a coordination number of 6, and that gives you an octahedral complex. We could do, for example, Cu H2O 6 2+. So when you're doing that, draw the central metal ion here, draw the dotted lines and the dashes and the wedges and all that stuff like this. And then you would just do it lone pair by lone pair. So OH2, lone pair, 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 H2O like that. And you draw your little square brackets like that and your big 2+ there. So this is a coordination number of 6. It's going to be octahedral as well, right? That's all of the possible ways we can really do things with monodentate ligands. What about if we had a coordination number of 4? So an example of that, well, there's 2 scenarios. You can either have a tetrahedral complex, and one example you guys need to know is CuCl4-. That's an important one there, right? Because that chloride ligand is too big. It's still monodentate, but it's too big, so you can only fit 4 around it. So what you end up having is you've got Cu and a dot and a wedge like this, and Cl ligand, and a Cl ligand, Cl ligand here, and a Cl ligand there. That's really poorly drawn, but that's what it would look like, and it is, 2-. However, you can also have other things with a coordination number of 4. Sorry, I should have written tetrahedral there. Tetrahedral. Because you can also have cisplatin or transplatin. So PT-NH32Cl2 is an example. So with cisplatin, it would be this. Out we go. Cl, Cl, NH3, dot lone pair, NH3. There. Right? So that's us talking about the shapes of monodentate ligands. But they also, so we've included our diagrams, so equations is what they want. So they want to show equations for ligand substitution reaction. So an example of a ligand substitution reaction could be, for example, here, you can see the coordination numbers change, so you can use that as your example. So Cu H2O 6 2+ plus some amount of Cl- ends up giving you CuCl4 2- plus the H2Os that have been booted off, 6H2O, 4 here, so it's going to be 4 there. And you would say the Cl- ligand has swapped with the H2O ligand. There you go. So propane is used as a camping gas. A student wants to look for the enthalpy of combustion of propane with these 2 methods. So they carry out this thing with the equipment below, give the answer to the enthalpy change of this propane in kilojoules per mole. So a lot of people get confused with this. Kilojoules per mole means that 1 mole would release or take in this much energy, cause an energy change of this much. When you're doing Q equals mc delta T, right, you're actually working out an energy change in joules, not per mole. The reason being is because the amount of moles that led to this energy change could be whatever, right? We always use enthalpy changes as 1 mole to keep things consistent, because 1 mole causes this much energy change in kilojoules. So if we want to work out the enthalpy change of combustion, the energy change that's happening is because it's being combusted. So we're going to work out each bit. So M is going to be the mass of the thing that's receiving the heat, right? It's not the mass of the substance. This M is going to be the mass of the thing losing or receiving the heat. We have 100 centimeters cubed of water. The density of water is 1 gram per centimeter cubed. So the M is going to be 100 grams. Every centimeter cubed of water is 100 grams. C is going to be 4.18. And delta T is going to be our final minus our original temperature, so 46.1 minus 21.6, which is going to equal 24.5 degrees Celsius, right? So then what we do is we put them in. So Q equals MC delta T, which is going to be 100 times 4.18 times the change in temperature was 24.5, which gives us 10241 joules. So that was the energy change. However, this is in kilojoules, so then the energy change could also be written as this over 1,000, so 10.241 kilojoules. However, this is per 1 mole of propane. We do not know how many moles of propane cause this enthalpy change. So what we need to do is we've got to work out the moles of the propane, which is C3H8, which is going to be mass over its MR. So we can work out the mass of the propane before and after burning. The mass of the propane would be the difference between these two because that's how much was burned to give you that energy change. So 99.218 minus 98.976 gives you 0.242. That was burned. Remember that this burning of the propane led to the energy change that we see. So the moles of the propane that we did burn to give you this energy change would be its mass, so 0.242 over its MR, which is 44, which gives you 0.0055 moles. That means 0.0055 moles caused an energy change of 10.241 kilojoules. Right? But they want it for 1 mole. So 1 mole does how much? Well, if you go from here to here, you've divided by that. So all you would do is 10.241 divided by 0.0055. If we do that, we get 1862 kilojoules per mole, but we're not done because we lost heat to the surroundings, so the enthalpy change is negative. So it's minus, and then we also need to stick to the number of significant figures they've told us, 3, so it's going to be minus 1860. There you go. A student finds that the experimental enthalpy change, delta C, for this is much less exothermic than an accurate standard enthalpy change in databases. One reason could be that this experiment had not been done under standard conditions, suggest two other reasons. Here, remember that Q equals MC delta T, and we divided that Q over its moles. So the enthalpy of combustion for this example here would have been Q over the moles, so it would have been MC delta T divided by the moles here. Now the questions found that theirs is much less exothermic, meaning that the energy change was less, right? We need to figure out what possible reasons there could be. So this value that we got was lower, so Q equals MC delta T was lower, right? So what could have happened is any one of these bits could have been screwed up. The M of the water could have gone, but we can't just say that, we have to say why it could have happened. The water could have evaporated, which means M would go lower, and that would make that lower. Alternatively, the moles that were actually burnt might not have actually been burnt, so as in, we would have had incomplete combustion, or delta T could have been screwed with where the temperature was lost to the surroundings. Can you see how mathematically it works out? You just need to put a reason to it as well. So any one of those really. So evaporation of water, or incomplete combustion. There you go. This question's devious because it hinges on all of the things that I yap about every single time I do a video where it's like, don't do a formula, use a cycle. And like everyone that did well in this used a cycle. So I'm just saying, cough, cough, you know. But anyway, it says the student determines the standard enthalpy change of combustion of propane using the bond enthalpies in this table. So combustion of propane, combustion, remember, is where you're doing 1 mole of a, whatever substance combusted completely in oxygen, right? So plus O2 gives you combusted products, right? Now, an experiment is not needed. We've got these bond enthalpies in the table. So bond enthalpy is where you've got 1 mole of a bond, blah, 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 blah. Eventually, it's broken right into atoms. So each one of these are the bonds, the left side here, and atoms. Fine. The bond enthalpies can be used to determine the standard enthalpy change of reaction for this equation. So you've got C3H8 plus O2 gives you CO2 plus 4H2O gas. That's not the enthalpy of combustion, because the enthalpy of combustion would have had a liquid here. This is a different enthalpy reaction, right? So each arrow in enthalpy cycle is always an enthalpy change, so that delta RH is here. They've also then told you the enthalpy change of vaporization, the standard enthalpy change of vaporization of water is the enthalpy change for the conversion of 1 mole H2O liquid into gas under standard conditions. And wow, would you look at that, they've given you it there, right? It says here, determine the standard enthalpy change of combustion of propane using this delta RH value for equation 3.1 and the vaporization of water. Right. So if we have a look, here we have gaseous stuff, all of them are in their standard states, and they've given us bond enthalpies. So what we could do is we could make an equation for this, like a cycle, right? So what I'm going to do is I'm going to write that whole equation again here. So C3H8 plus 5O2 gives us 3CO2 plus H2O, 4H2O. But then this is gas, that's gas, that's gas, and that's gas. Right? That's going to be delta HR. They've given us bond enthalpies in the table, and all of these are the bonds that would have been broken, and these are all the things with the bonded stuff in it. So what I could do is I can construct a cycle with the elements down here that have been broken, the broken bonds, if you will, right? And then, if we're doing bond enthalpies and all the bonds here, the arrow is going down, bond enthalpy and all of this, the arrow is going down, the arrow is going down because we're bond enthalpying, and it's going down here as well. Now, here, we can start putting the numbers in, because if you have C3H8, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, right? That means we're going to have 8 CHs, and we're going to have 1, 2 of them. So that means we're going to have 2 lots of 3, 4, 7, plus 8 lots of the CH, which is 4, 1, 3. Here, 5 O2s, so it's, there's 5 lots of that, so 5 lots of 498. Here, that's 3 CO2s, so there's 2 COs for each of them, there's 3 of them, so it's going to be 6 of 805. And here, this is H2O, so we're breaking 4 lots of 2 lots of the OHs here, because each one of them has 2, so it's 464, so it's going to be 8 lots of the 464. So 8 lots of 464, right? So that means, yeah, Hess's law says if you start and finish at the same point, the entire route is the same, as in the enthalpy change for that start and finish will be the same for this whole thing around. So that means that the enthalpy change of reaction would equal, so going down with this arrow, 2 lots of 347, plus 8 lots of 413, right? Plus 5 lots of 498, because we're going that way. We're going against these arrows, so minus 6805, and then minus 8 lots of 464. If we do that, delta HR will equal, delta HR then is minus 2054 kilojoules per mole. But the question wants you to find what? The enthalpy change of combustion of propane. The enthalpy change of combustion of propane, the formula, remember, for this is going to be C3H8, because you're combusting 1 mole of this substance in its standard state under standard conditions, blah, 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 right? Plus 5O2 makes 3 CO2, that's gas, plus 4 H2O, a liquid. That's the enthalpy change of combustion. This has a gas here, so it's not the same as the enthalpy change of combustion. What you should do is then compare your enthalpy of combustion equation to the one we just had. The only difference here is that this is a gas, this is a liquid. So write that down. Is that the enthalpy change of this reaction was H2O gas, and that gave us minus 2054, remember? The enthalpy change of combustion, though, is different because it has H2O liquid. That's where this comes in, because this equation has told you that if you have H2O liquid and you become H2O gas, then the enthalpy change for this to vaporize that is plus 40.65, right? If we want to use this equation and come back down to a liquid, then we're going to go the opposite way. We're going to undo that vaporizing, as in take this out. However, this is for 1 mole, we have 4. So then the enthalpy of combustion is going to equal minus 2054 minus 4 lots of this, because we're going from gas to liquid the opposite way. So minus 40.65, but then there's 4 lots of them. If we do that, we end up getting, which gives you roughly minus 2216.6, so roughly minus 2217 kilojoules per mole. This question really hinges on you knowing your enthalpy definitions, and you've got to be very careful with that, and that's why I say cycles and definitions are important. But there you go. So a student carries out an investigation to identify 2 metals M and X, but 2 different methods. So they're given metal M, they analyze it using a back titration technique. This is then used, but this is reacted with excess acid. It's titrated to find out how much acid is left in the reaction. So stage 1, they add this much HCl to this M. An excess of this has been used so that all of it reacts, and then a redox reaction occurs, and you get an M in the +2 oxidation state. And then what they do is they then add 25 centimeter cube sample of this diluted solution with NaOH, and then the NaOH reacts with the excess HCl, and you get this, and the student repeats the whole titration to get concordant results, and here's their results. The trial tide has been omitted. The burets have been read to the nearest 0.05 centimeters cubed. You guys should be happy in OCR that you get this broken down, because AQA gets it in one massive chunk of text, and yeah. In stage 1, a redox equation is taking place between M and HCl forming hydrogen and a solution containing M in the +2 oxidation state. Write an overall equation with state symbols and then write half equations for this. So the overall equation they've told you was it was solid M that they'd reacted it with. Write down what you know. If we've added HCl, we are then making, well, H2 gas is one of them. What's left is Cl and M in the 2+ oxidation state, so it's probably got to be M 2+, Cl-, so Cl2, right? And it's aqueous because it's dissolved. This will have been aqueous to begin with, that's solid. To balance this out now, well, there's 2 Cls here and there's H2 there. So we're going to put 2HCl there. Now the oxidation equation then, so if you look at M has gone from 0 to +2. So it's M solid has become M2 plus aqueous plus 2 electrons. When you have something that's oxidized, something else has to be reduced, hence here. So somewhere in this has to have been reduced. I can see this elemental hydrogen here that wasn't here, so that's screaming to me that that would have been it. So that means we will have made H2 gas here, right? And for it to have been reduced, well, we can see it's H plus here. So it would have been H plus, and you can see that that's 2H plus because there's 2 of them there and there's 2 there. Each one of them wants 1 electron, so it's going to be 2E minus like that. There you go. So in stage 1, suggest 2 observations that would confirm all of this M has reacted. So if we have a look at where M is in this question, so stage 1, they add M to this and they keep adding excess HCl. Well, we've just been told that it makes hydrogen gas as well. Observations means what do you see in the lab? As in, it doesn't mean you can just record something or measure something. It's as in what do you visually see? If it's making H2 gas and it's all reacted, then your fizzing is going to stop, isn't it? It's going to stop fizzing gas. So fizzing stops. You don't just say no more H2 produced or whatever. That doesn't show what you're seeing. To also make sure it's all reacted, it seems really goofy, but it's also that the M solid will have all disappeared as well. That's what they're asking you, nothing more. In stage 3, write the ionic equation for the reaction taking place in this titration. So if you look at stage 3, what are they doing? They've got this diluted solution from stage 2 and they've added NaOH. You'd be surprised how many people just look at that and they're like, I have no clue what to write. Cough, cough, the sentence before is kind of helpful. The resulting, so a 25 centimeter cube of this diluted solution from stage 2. What did they do in stage 2? They made it up to distilled water and people are still like, I don't know what I'm doing. Go back one more step. An excess of HCl has made sure that this is all reacted. So we've got an excess of acid and we're adding NaOH. Acid plus a base neutralization. So it's H plus OH minus gives you H2O. There you go. Metal M can be identified in these steps. The amount of moles in the excess HCl it reacts with, that remains after the reaction of M with HCl, the amount of moles of HCl it reacts with M, and the identity of M. Oh, you guys are so lucky, bro. You got given it nicely. Like, presented beautifully. Go look at an AQA question if you want some more practice on this, because the AQA ones are just a massive, huge piece of, text, and they're just like, enjoy. So you guys actually get nice steps for this. What we need to do is figure out how much HCl there is. But what I'm going to do is I'm going to just have a look at the story again and make sense of it because there's a lot going on here, right? What they've done is they had 6.90 grams of M, right? So M2 plus the acid, right? Some mysterious thing here. Then what they did is they took 25 centimeters cubed of this thing and then they reacted it with NaOH. So in this, the HCl is going to be reacting with the NaOH. As a mixture of that plus the acid will have reacted. Plus NaOH, right? Cool. Do we know anything else about the NaOH? We know that it has a concentration of 0.320. And we also know that that acid, wherever it's gone, had a concentration, the HCl had a concentration of 2.10 moles dm minus 3. And we also know that we used 100 centimeters cubed of it. Fine. And then we need to figure out how much NaOH they'd used. Well, here, the titration results are here. The titration results would be what was, the NaOH, because they're adding NaOH using the titration. So what we need to do is we need to figure out the volume of NaOH using the mean titer. So the mean titer would be all of the concordant results, so within 0.1 of each other. Here, they're cheeky because they're not actually giving you the titer. You need to work that out, initial minus finals. So all your titers are going to be 27.30, 27.55, and then this is going to be 27.20. The titers that are concordant are here and here within 0.1 of each other. So it's going to be 27.3 plus 27.2 divided by 2, which means it's going to be 27.25. Don't just write numbers down and be like, oh, I'm lost. I don't know what I'm doing. That is the volume here of 27.25 centimeters cubed. Now we can work backwards and figure everything out because I know all of this will have reacted with all of that acid. So the moles of the NaOH would equal the moles of this Cl in a 25 centimeter cube sample, right? So then that's just going to be concentration times volume. So it's going to be 27.25 divided by 1,000 or times 10 to the minus 3 times its concentration, which is 0.320, and that gives you 8.72 times 10 to the minus 3 moles. So now we know how many moles of HCl was in here. So then the moles of HCl in 250 would have been your answer times 10, which is going to be 8.72 times 10 to the minus 2 moles, would be the total that we added to begin with minus this that was left behind, because this is the amount that was left behind. This moles is in that 250 though. Remember that 250 is M2 and leftover acid. So we know how much of the leftover acid there was, but we don't actually know how much went and reacted with this. However, we know that M was mixed with a hell of a lot of acid there. So we can work out the moles of the acid initially that was added, right? Which would be its concentration, so 2.10 times its volume, which is 100 over 1,000, so times 10 to the minus 3. If we do that, we get 0.21 moles. So that's all of it that we had. However much was left was this here. So the moles that actually reacted, the moles that HCl reacted, must have been 0.21 minus the 8.72 times 10 to the minus 2, which if we do that, we get 0.1228 moles. Cool. Now we need to figure out the ratio of what M to HCl was. There's multiple ways we can figure this out. I mean, here we wrote an equation for it. And also, it makes 2 plus, Cl minus. So that means this is in a 2-to-1 ratio of HCl to M. So the moles of M is going to be half of this thing. A half times 0.1228, which is going to be 0.0614 moles. To figure out the metal now, well, we know the mass of the M was, wherever it was in the question, 6.90 grams, 6.90. So MR equals mass over moles, which would be 6.90 divided by 0.0614, which is roughly 112.4. If you look at your periodic table, the mass that matches is cadmium, which is Cd. There you go. The student is provided with a carbonate of an unknown metal, and they measure the mass loss when X2CO3 is reacted with an excess of HCl in this equation shown below. So what they did is they added HCl to a conical flask, they weighed it, they added this, and then immediately reweighed, and then they weighed it 5 minutes after. So conical flask and HCl, and this right before you've reacted, and then after. So we can work out the moles of the CO2 because all of this decrease must have been CO2 lost. So that means the mass of CO2 lost would have been these two subtracted, which is going to be 2.75 grams. The moles of CO2 would just be mass over MR, which is 2.75, divided by this thing's MR, which is 44, which gives you 0.0625 moles. Cool. Now it says work out the molar mass of X2CO3 and identify metal X. So all of this CO2 must have come from X2CO3. So X2CO3 eventually will have done whatever, right? And eventually would have put out a CO2, right? So if we have the moles of CO2 to equal 0.0625, then that must mean that the moles of the X2CO3 must also be 0.0625. We could try and work out its molar mass by working out how much we had to begin with. If you have a look, we have the conical flask and HCl, and then conical flask and HCl and X2CO3. So this mass of X2CO3 is going to be the difference between these two now, which is going to be 187.5 minus this. So if I do 187.50 minus 172.93, we end up getting 14.57 as its mass, 14.57 grams. We now know its moles, so we can do MR equals mass over moles, which would be 14.57 divided by 0.0625. That's roughly 233.12, so 233.1. And it's going to be, if you look at the periodic table, it's rubidium. Done. After analyzing the results, the student was told that their molar mass is incorrect. The student evaluated the experiment to see if there were any reasons for the incorrect results, and the student wondered if the reaction was complete when this had been recorded after 5 minutes. How can they modify this to be confident that the reaction had been done? When this reaction is happening, what you're doing is you're losing CO2, as I've written there, and the mass is going down. So all you could do is just keep reweighing it again and again and again until it's just no longer changing. That's it. So you would reweigh until the mass is constant, because that way you know all the gas to lose is lost. The student finds out that carbon dioxide is slightly soluble in water. Stay and explain how the solubility would affect the calculated molar mass of this. So what this experiment's assuming is X2CO3, eventually blah, 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 whatever, right? It makes CO2 gas. It's assuming that all of this has been lost, right? If all of that's not actually been lost, some of it's actually been, dissolved, well, immediately you can write that the moles of CO2 that was lost would decrease. It'd be smaller, because some of it's actually left behind and stayed, dissolved. So then what we need to do is figure out what impact that would have on here. So if we track back on all the things we did here, we figured out the moles of the CO2. We then were like, okay, well, all of it must have come from here. So these are 1-to-1. All of the moles of CO2 came from here. So if we have less CO2 actually being released as gas, then that means that the moles of the X2CO3 would also be lower, right? So that means the moles of X2CO3 would be lower. But since MR equals mass over moles, can you see how that's smaller? The MR gets bigger. So the MR would actually be higher, and you'd turn that into words, obviously. The molar mass would actually be greater. There you go. The equilibrium constant Kp and the temperature T in Kelvin are linked by this mathematical relationship shown in this equation, where the gas constant is in joules per moles per Kelvin and delta H is the enthalpy change. The table shows the values of Kp at different temperatures for an equilibrium. Complete the table by adding these missing values. So Kp So we've got missing 1 over t's. All we've got to do is just do 1 over 500, 1 over 600, 1 over 700, 1 over 800, and then keep it to the number of significant figures and put it in standard form as well. So if I just skip through this real quick, 1.67 times 10 to the minus 3, 1.43 times 10 to the minus 3. Right, so there's our temperatures. I know that's 2, but you have to put 2.00 because you want to keep it the same number of decimal places so the table's readable. Otherwise, if you're mishmashing, like, you know, the number of, like, what's the word? Like decimal places and significant figures, it's just going to be an absolute pain in the ass to read. So don't do that. Make sure you have them matched like that. Then ln kp, all you do is you take the kp value and you put ln and then the number there. So if I do that, and there you go. There we go, that's done. And there's no decimal places for each of these, so that's fine. Because that one's not giving you any decimal places, so you wouldn't add any extras. So it says state and explain how increasing the temperature affects the position of the equilibrium and whether the forward reaction is exothermic or endothermic. So you can't just look at delta H to be like, oh, it must be up or down. You've got to look at what the effect on Kp is with temperature. So can you see how ln Kp here is dependent? If you see here, ln Kp is dependent on 1 over T. So if I increase the temperature, can you see how ln Kp or Kp would go down, the number, right? Increasing temperature means that this fraction would get smaller. So that means, well, you know, first of all, start by saying that increasing the temperature would cause eventually Kp to decrease. Now if Kp is decreased, that means you have less products over reactants. Therefore, the equilibrium must have moved which way? The equilibrium must have shifted to the left. Therefore, again, if you increase the temperature and it's moving to the left to make the temperature go back down again, the forward reaction is exothermic because the reverse one is endothermic in an attempt to try and absorb that extra heat. There you go. Now it says plot a graph with the axes on the opposite page. Use your equation to find delta H for this equilibrium and then give it to 3 significant figures. So if I just have a very nicely plotted graph. Okay, so just for the sake of time, I've just put the mark scheme 1 in here just because it would take me ages to do this and I'm kind of churning out these videos and also this tablet's annoying. But yeah, you would plot the graph like this, it's going to be a straight line, right? Now it says here to use this graph and your equation to determine delta H in this equilibrium. So let me just quickly scribble down what this equation was. So ln Kp equals minus delta H over R times 1 over T. They've actually written this so nicely. What? Plus delta S over R. Every single straight line equation obeys y equals mx plus c. Y is the y-axis, m is the gradient, x is the x-axis, and c is, you know, the y-intercept. So look at what you've changed your y to. So our y now has become ln Kp, and our x-axis has become 1 over T. I've cropped it out by accident, right? But our x is 1 over T. Rewrite this now with the new things. So ln Kp equals m times 1 over T, right, plus c. Then compare to the original. M times 1 over T, this times 1 over T. Can you see m has to be this? M has to be minus delta H over R, right? Because that's times 1 over T, and c, the y-intercept, is this, right? So c has to equal delta S over R. M is the gradient, so that means the gradient's going to be this. So what you would do is you'd pick 2 points on a graph, you'd work out the y step over the x step, and you'd get that. So you do y2 minus y1 over x2 minus x1. Let's pretend I've just mysteriously done that. So let's say I've magically done that, and I end up getting my gradient to be 57000, right? So that therefore means, if I just move here, minus delta H over R equals 57000. So then delta H would be minus R times this whole thing, which gives us, it's going to be minus 473898. So then they want in kilojoules per mole, so it's going to be delta H is going to be this divided by 1,000, which is minus 474. We'll do it to 3 significant figures. There you go. So minus 474. So yeah, there's that. That's with a gradient, like of the lower range of the answers. It allows any gradient from 57,000 to 63,000. Then you just rearrange it like that. There you go. Then it says explain how delta S could be calculated. Well, we just said that the y-intercept from before is equal to delta S over R. So you can find y-intercept by extrapolating the line. I'll talk about what that means in a sec. Then times by R. So extrapolating is where you just extend the line to eventually, you know, find where that y-intercept is. So what you would do is you take this line and you'd extend this line longer and longer and longer and longer until it crosses the y-axis here. That's extrapolation, where you're taking that line and taking it further. Obviously, I've drawn that horrendously. That y-intercept will tell you delta S over R, and then you can just, you know, times it by R to find delta S. There you go. So this question's about 2 different types of acid found in organic compounds, carboxylic acid and sulfonic acids, as shown here. So we've got carboxylic acid, sulfonic acid, nice. So let's complete table 6.1 to predict the bond angles A and B and name the shapes which makes these bond angles in the functional groups of carboxylic acid and sulfonic. So it's all to do with the number of lone pairs and bonding pairs, right? You can treat double bonds as if it's just a singular bonding pair, right? So we have one bond here, one here, and one here, no lone pairs. So we have 3 bonding pairs, 0 lone pairs. The angle for that is going to be 120 degrees, and that is trigonal planar. You can treat single bonds and double bonds alike when you're working out shapes. For sulfonic acid, they want the angle around this, not like here and here and here, right? So we can't just jump and say, oh, there's 1, 2, 3, 4, 4 bonding pairs or low pairs. We're not doing that because we're doing it around this one here. So around this oxygen, it's got 1 covalent bond here, 1 covalent bond here, right? But it's got 2 extra lone pairs like this because it's in group 6, 1, 2, 3, 4, and then 5, 6, and the other 2's from there. So that means it's got 2 bonding pairs and 2 lone pairs. So that means it's 104.5 degrees and it is bent or nonlinear. So you got to be careful. It depends what it's around and what the bonding pairs and lone pairs are around. Ethanoic acid and methane sulfonic acid are both monobasic acids, and the pKa's are shown here. A student suggests that 1 mole per decimeter cubed of the CH3SO2OH should have a lower pH than that here. So it says, write an equation showing the conjugate acid-base pairs for the equilibrium of this with the water, and then explain with reasons if whether they're correct. An acid is anything in the universe that is able to lose an H+, and a base is anything in the world that can react with an H+, a proton donor, and a proton acceptor. So here it's saying, show that this is, its conjugate pairs with water. So write down what you know. We're now going to react CH3, SO2, OH, and we're adding water, and it's going to be an equilibrium. So something's losing an H+, and something's gaining it. In the structures from before, the most likely H+ that's going to be lost is that, rather than all the other CH3 bits. So that means that this is going to lose an H+ to become CH3SO2O-, but in the same thing, something else has to accept that H+, it can't just disappear. So you end up getting H3O+. Because this has lost an H+, this is an acid here. Because this can gain an H+ to become back here, that's a base. Because this has gained an H+ to become this, that's the second base. This has got an H+ that's extra, it can lose it to become that. So that is your second acid. It hinges on you just appreciating anything that gains a proton is a base, anything that loses it is an acid. End of. That's how it works. So now we've done that part, and then it says explain with reasons whether they're correct. Okay, so with H+, we need to have a look at, pH is all about H+, right? And these are both weak acids. If a weak acid will have this dissociation thing going on, if it's just an acid on its own, squared over HA, right? If there's more H+, that means it will have dissociated more, because every weak acid dissociates into this, right? More H+ means Ka is going higher, because more H+ means more acidic, right? So if I just say, if we have more H+, we'll have a lower pH, but that means we'll also have more of this here. So it means that Ka would be higher, meaning more dissociation here, right? So then pKa, so what we can do is we can compare these Ka values between the two. Now because pKa is negative log to the base 10 of a Ka value, it's a bit tricky doing all of that, comparing them like this. So because we're looking at Kas, I can just do 10 to the minus 4.76 for this to undo it, and then 10 to the 1.9. Immediately you can see that Ka is bigger here than here, because that's 10 to the minus that, and that's 10 to the positive. So this has a bigger Ka, meaning that there's more H pluses, which means it must have got a lower pH, and that means it must have more, dissociation. And that's what you're going to say, basically. You just turn it into words. So that means that the CH3SO2OH has a lower pKa, but that means it's actually got a higher Ka, therefore there's more H+, therefore there's more dissociation, therefore it's got a lower pH, and therefore is a stronger acid, because it's dissociated more, than the CH3COOH like that. There you go. Carboxylic acid and sulfonic acids can form esters, so for a carboxylic acid ester, right, that's C+OOC, you're probably going to end up something similar here. Let's have a look. Sulfonic acid esters can be hydrolyzed by aqueous alkali. The equation shows the alkaline hydrolysis of this. So you've got CH3SO2, OCH3, OH, and then it gives you this and this, right? It says, in the boxes below, add curly arrows to show the mechanism for this reaction. In the first box, the hydroxide ion acts as a nucleophile. Fine. So have a look at each box and see what's happening between all of them, right? From here to here, what's changed? This double bond's gone. It's a single bond here. This has extra electrons. When a bond breaks or is made in mechanisms, you have to show which way the electrons have gone. You can't just make them disappear. So that means this bond must have done that. It has to have broken like that. There's no other way to get electrons here and make that disappear. But if you also look, this S now has an OH on it. A new bond is formed here, meaning a transfer of an electron, electrons have happened. So that means if this is acting as a nucleophile, it's giving its electrons to the S like that, and that's where that bond comes in, right? Now, if we look from here to here we have a double bond again. So these electrons must have gone back in here to remake that double bond. But can you see how there's OCH3 here, but now there's only OH? We must have booted off the OCH3 entirely. When you break bonds, remember, you have to show the transfer of electrons. So this bond's broken, those electrons must have all gone here like that, which is where that lone pairs come from, and there you go. Right? But we're still not done. Because if you have a look, the final thing we end up making is CH3SO2O minus and CH3OH. We're still not done though, because if you have a look here, can you see how we end up making HOCH3 and then this with an O minus here? So if you compare here and here, this bond has broken off. Electrons will have gone somewhere. So you can't draw it like this, because then that would end up giving H minus, and that'd be a plus. The electrons of this bond must have gone to this oxygen here, like this. And then, if we have an HOCH3 here, this H must have bonded onto here, so those lone pair of electrons must have gone to the H like that. And there you go. That's how you do it. With mechanisms, when you're breaking and making bonds, you have to show which way the electrons are going, and you can just kind of work it out logically by doing it, thinking in my head, well, I mean, this has happened, and this has happened, it's turned into this. There you go. Anyways, I hope that helped. Please like, share, and subscribe. You know the drill. Thank you.